Okay, we are on to the very final chapter now of Applied Year 2, Chapter 8. This is Further Kinematics, and it's basically everything to do with like movement. That's what kinematics means here. We did some of this in Year 1 with like the constant acceleration formulae and variable acceleration. We returned to it in Year 2, and it's mostly vectors, but I'll tell you some of the other parts that pop up as well. So the first thing that I really want you to do in these kinds of questions, if you see one, it won't tell you what techniques you need to use. So you need to categorize the question and decide about the acceleration. Is it the first kind where there's zero acceleration? In other words, there's constant velocity. This is a very rare type of question that used to come up a lot in the old spec, but hasn't come up in the new spec, but it is in the textbook. So I do want to cover it. The second kind of category would be if the acceleration is constant. That's where we're going to use things like SUVAT formulae, and then variable acceleration. We know from Year 1, variable acceleration, you use calculus, differentiation and integration. So this first question that we have is a zero acceleration or constant velocity question. And what we do for these kinds of questions is we adapt our GCSE formula for distance equals speed times time to give these new versions where distance is now represented by displacement, which is the vector r. These are in bold, so they're vectors. We still have the velocity, which is a vector in bold, and then time is a scalar quantity, so I haven't put it in bold here. If you were going to be writing these things, you should be underlining them like this. And there's a slightly adapted version of this. Because this is talking about the displacement, if we wanted to describe its position vector, we can add on its initial position. This r0 that we have here is the initial position, because its final position would be its initial position plus its displacement. So you can kind of decide which of these that are needed. I tend to use this one. Lots of the time it might start at the origin, so we don't need this. And I will read through this now, and we'll probably be using it over the next few questions, so I'll demonstrate how it works in practice as well. So it says if the particle is north or south or northwest, basically a compass direction of O, then its position vector is a multiple of a vector describing that compass point. So if it's talking about where it is, we're talking about its position vector. If a particle is moving in or traveling in a particular direction, then we would say that its velocity vector is a multiple of that direction vector, obviously because moving or traveling is to do with velocity. If a particle is accelerating in a particular direction, then its acceleration vector is a multiple of that direction vector. So we're only going to probably be using this first point in this question, okay? So let's have a look at this one. It says, in this question, I and j are horizontal unit vectors due east and north, respectively. Pretty standard beginning of a question there. It says that a remote-controlled red toy car is travelling across a large horizontal field with constant velocity. Now, we knew it was constant velocity because of the theme of this first slide, but as soon as you have that, that should be telling you we're going to be using these formulae. And it actually tells us what that constant velocity is. So I'm going to write it down. I'm going to do it in column vectors. You don't have to do it in column vectors, but if you do, you will not get penalized for it. I just think it's a much better way of organizing your thoughts with the I and j written in this form. The red toy car is modelled as a particle, meaning we can ignore its dimensions. At time t equals 0, the red toy car is at the point -8 minus j meters relative to a fixed point O. And it says find the time when the red toy car is northwest of O. Well, this thing, it's saying t equals 0, this is where it is. This is actually talking about its initial position. So its initial position is -8 minus 1 that we have here. And we want to find the time when the toy car is northwest of O. Okay, we'll come back to that in a second. But if it's northwest of O, we're going to be using this point here. We want to say that its position vector is going to be a multiple of a vector describing that compass point. So we need to find a position vector, and we're going to use this version, okay? We are going to say that r is equal to r0 plus the velocity multiplied by the time. So the position vector is its initial position, which is -8 minus 1, plus the velocity, which is 0.5 multiplied by t. Now, I personally like to get this all combined into one single thing here, so that I have it as a -8 plus 2t and a -1 plus 0.5t. So we've got its position vector. Now we want to find out when it is northwest of O. So I'm going to draw a quick sketch. Here is O that we have that's right in the middle. Northwest, thinking it like a compass point, is up here, right? It's exactly along this line. So if I wanted to describe this as a vector, we just need to do something that is in that direction. It doesn't need to be every single vector, but just one of them. So I could say something that's northwest is this little vector here where I've gone 1 to the left and then I've gone 1 up. So I can now say that a northwest vector is going to be 1 to the left and 1 up. And I'm going to be using that for this next part because we're now going to show that its position vector is a multiple of this one. In other words, it is parallel to it. We know that if we have two vectors that are parallel, then we can say that one is a multiple of the other. So I can now say that minus 8 plus 2t and minus 1 plus 0.5t is a multiple of minus 1, 1 that we had. And I'm just going to continue with this working out over here. So we have, looking at the I part, we have that minus 8 plus 2t is equal to minus k, and then minus 1 plus 0.5t is equal to k. You probably don't need to do this with k. You could just say like, oh, clearly the bottom one is the same one as the top negated, but I find putting k in here means we have a foolproof method for never getting it wrong. So I'm going to substitute. I'm going to take this part and substitute it in here. So minus 8 plus 2t is equal to minus 1 plus 0.5t. That's minus 8 plus 2t is equal to 1 minus 0.5t. I'll put the 0.5t on this side. I will add the 8 to this side, and I will just do 9 divided by 2.5 on my calculator, and I get 3.6 seconds. Now, I would probably do this to check in the exam. I would actually substitute 3.6 into this expression and see if it is actually northwest. So if I do minus 8 plus 2 times 3.6, I get minus 0.8. Okay, this is the position vector. We don't have to do this, but I'm doing it as a check. And then I'm also going to substitute 3.6 into this part. So it's minus 1 plus 0.5 times 3.6, and I get that the position vector is 0.8. So if we think about what this is actually representing, if we have the origin, and we're saying we're going minus 0.8 up 0.8, we're saying that the particle is now at this point, which is clearly northwest of the origin. So I'm going to just say that this part, I'll do a little scribble through it because that was just me doing some checking. And then we've got an interesting part of the question that comes up because it now has introduced another car. It says a blue toy car is also travelling across the same field, but with constant velocity 0.3i plus j meters per second. At time t equals 0, the blue toy car is at the point 5.6i minus 5j relative to O. Show that the toy cars collide and determine the position vector of these the collision, relative to O. So the red car that we had is this minus 8 plus 2t and minus 1 plus 0.5t. I'm going to try and now set it up for the blue car. So for the blue car, I'll just box this off. We've been told that its velocity is 0.3 and 1, and that its initial position, I'll tell you what, I'm going to use the letter B for this. Its initial position was 5.6 minus 5. 5.6 minus 5. So if I was going to find out what the blue car is, it would be the initial position plus its velocity times by time. So that is 5.6 minus 5. I'm actually going to do this all in one single line. That's going to be the velocity times by time. You're imagining these things getting multiplied by t. And then this would be a minus t as well. So you can jump straight to that. Now, if they collide, then they're going to be in the same position at the same time. So I'm going to say collision. They will have to have the same position at the same time. And I need to show that they're in the same position at the same time. So if I want to show they have the same position, I'm going to make their position vectors equal to each other. So I'm going to have my minus 8 plus 2t and my minus 1 plus 0.5t. And the blue is 5.6 plus 0.3t and minus 5 minus t. So if I have a look at the I components, I get that minus 8 plus 2t is 5.6 plus 0.3t. So I shall subtract the 0.3t, so I get 1.7t is 5.6 plus 8, which is 13.6. And so t is 13.6 divided by 1.7, which is 8. Okay, so now I know they have the same I component when t is 8. But I need to check the t component to show that they have the same position at the same time. They have to have the same I and j positions. So for the j positions, I have minus 1 plus 0.5t is equal to minus 5 minus t. So if I add the t, I get 1.5t. And if I do minus 5 plus 1, I think I've done something wrong with the way I've written this, haven't I? Because the velocity should have a plus here. I hope we've noticed that. The velocity has a 1, and I had done it with a minus. So I'm just going to quickly go through and do this. And you can tell how I knew I'd got it wrong, because I was going to get that minus 1.5t was equal to minus 4, and I was not going to get the same time. And I know that they do actually collide. So it's good. I'm going to keep this in because I think it's useful for you to see how I know when I've made a mistake in a question. Okay, so I'm now going to subtract the 0.5t, so I get 0.5t, and I'll add the 5 to this side, so I get 4, so t is equal to 8. So I'm just going to do a little sentence to say they have the same position when t equals 8, so they collide. And I will say that the collision point is, and I can literally now just substitute t equals 8 into either this one or this one. They will give you the same thing, and you can check to see that that works. So I'll do minus 8 plus 2 times 8. So I'm going to do minus 8 plus 2 times 8, and then I'll do minus 1 plus 0.5 times by 8. So our answer is going to be minus 8 plus 16. That's an 8. And then I shall do minus 1 plus 0.5 times 8, which is 3. So find the position vector of the collision. So there is our answer that we've got. They collide 8, 3. And you could write that as 8i plus 3j if you wanted to. Now, I just wanted to quickly mention this here. I don't cover vector projectiles in this chapter summary. You can, and probably should, convert those problems to normal projectiles problems. And I've touched on that briefly in the projectiles chapter summary. I kind of don't think it really should be in this kinematics topic, but it is covered. But just be aware that you still use your normal techniques for this. So when I say normal techniques, I mean just the collision techniques. If we have a question where we identify constant acceleration, instead of adapting these GCSE formulae of distance equals speed times time, we adapt our SUVAT formulae. So we would normally have S equals ut plus a half at squared. We tend to use r for displacement. Or you have this adapted version where you're then able to take into account its initial position. This one is just saying the displacement from where it started. This one is saying this is where it is after this displacement has occurred. Or v equals u plus at. This t probably should not have been made bold. Obviously, it's just the v, the u, and the a that are the position vectors for these parts. And there are other vector versions of the SUVAT formulae, like s equals u plus v over 2t, and s equals vt minus a half at squared. You can turn those into vector ones, but you can't turn v squared equals u squared plus 2as, because we can't do v squared or u squared with vector quantities, okay? A little exam tip here. If you want to convert from a vector to a scalar, we remember from normal maths that we just use Pythagoras to do that. So, big clue in the question, it is constant acceleration. I'm immediately going to write that down, that the acceleration here is 4 minus 2. And it tells us that when t is equal to 0, p is moving in the direction of 3j. Here we go. It's now this thing. If it's moving in the direction, then its velocity vector is a multiple of that direction vector. And because it's when t is equal to 0, I think this is going to be to do with its initial velocity. It's moving in the direction of 3j, so I'm going to multiply it by something. I'm going to say it's a multiple of that. In other words, it is just 0, 3k. And at time t equals 0, p is at the origin, so I can say that its initial position is just 0, 0, which is very helpful in a question, makes it nice and easy. And when t is equal to 3, its position vector is 18 minus 7. And the question wants us to find the speed. Interesting, I think we're going to be using this part down here. The speed at time t equals 5. So if we tried to dive straight in and use our formula v equals u plus at, where we're going to try and find out its speed when t is equal to 5, we will get 0, 3k for the u part, and then the acceleration, which is 4 minus 2 multiplied by 5. And the trouble here is that we have this k that's in here, so we're going to have to do something to figure out what that is. I'll come back to this once we've figured out what k is. Now, there is another piece of information we haven't used yet, which is this part down here. So I can connect all of this together. I can use my r equals r naught plus ut plus a half at squared. Now, this is the position that it's in, okay? We know that when t is equal to 3, we know that its position is 18 minus 7. So I'm going to start substituting that so that we get 18 minus 7 is equal to its initial position, which is just 0, 0. I'm probably not even going to write it because there's no point in it being there. And then we get ut. Now, we've said that u is 0 times 3k and that t is equal to 3. And then I'm going to have a half times by the acceleration, which is 4 minus 2, times by t squared, which is going to be 9, or 3 squared. So just do a little bit of tidying up here. We get 18 minus 7 is equal to 0 and 9k. And then we're going to do a half times 4. A half times 4 is 2. 2 times 3 squared is 18. A half times minus 2, that's minus 1, times it by 9, is minus 9. So that's pretty good, because from the I part, we get that 18 is equal to 0 plus 18. Okay, well, that's good. And now we can actually find out what k is, because we get minus 7 is equal to 9k minus 9. Plus the 9 onto this side, and divide by 9, so that we get k is equal to 2/9. So now I know that k is equal to 2/9, I can actually figure out what u is equal to. So let's go straight over here. This is going to be 0. We have 3 multiplied by 2/9, and then we have the 4 times 5 and the minus 2 times 5. So the velocity is, when t is equal to 5, 20, and 3 times 2/9 minus 10, that is minus 28 over 3. So now we know that when t is equal to 5, we have found out the velocity, but we don't want the velocity, we want the speed. So to find the speed, I'm literally just going to do Pythagoras. So I will do my 20 squared. I personally just ignore the negative sign because it just feels like extra typing. So I'll do 20 squared plus 28 over 3 squared. Square root my answer, and I get that the speed is 22.0705 or 22.1 meters per second to 3 significant figures. Okay, let's have a look at what part B is. I've taken up so much space there. It says when t equals 3, p is at c. Okay, so when t is equal to 3, I'm going to say it's position vector of c. I think we've actually been told that when t is equal to 3, this is where it is. It is at 18 minus 7. So we now need to find out, it says when t is equal to 6, p is at d, find the distance cd. Okay, well, I'm going to use this formula that we had here again, okay? I'm going to be using r equals r naught plus ut plus a half at squared. Now, r naught was just 0, 0. U was 0 and 3k. 0 and 3 times 2/9 is 2/3. So there's the ut. And then we're going to do a half of a. Half a would be 2 minus 1. So that's 2 minus 1 multiplied by t squared. Oh, look, I didn't even put in the t that was supposed to go with u there. So now I can say, let's find out what the position vector is when t is equal to 6. So this is where d is going to be. Well, I'd have 0 times 6 plus 2 times by 6 squared. And 2 times by 6 squared is 72. And then I'll do 2/3 times 6 minus 1 times 6 squared. I'm just looking at the j components of these ones here, and I get minus 32. So now that I know that c is this and that d is this, I'm trying to find out the distance between c and d. So to find the distance, I shall do the vector cd, which we know is d minus c. You could do c minus d as well, it would be fine. And so I shall do 72 minus 32 minus 18 minus 7. 72 minus 18 is 54. And careful here, minus 32 minus minus 7 is minus 25. And so the distance CD is going to be Pythagoras with 54 squared and 25 squared, which on my calculator is 59.5 meters to 3 significant figures. So we found out the distance between them. So I've done a lot of this thing of Pythagoras converting here. So we had to do it with the speed. We also had to do it with the distance here. Okay, variable acceleration. If we have variable acceleration, it is the exact same stuff as year one. You use calculus. What I've said in year one is you write down the letters S, U, V, A, T, the order of Suvat. Apart from in this time, we might be looking at some vectors. We often could write that with R, or we could write that with X. So just you need to be aware that if you have R or X, it's still a displacement. And to go down that list, we know that you have to differentiate, and you differentiate with respect to time. And if you want to go up that list, you want to integrate it with respect to time. Now, be prepared for year two integration and be prepared for calculus with vectors. I'm only going to cover calculus with vectors because this video is not covering variable acceleration questions that are the same style as year one, but with year two integration, because it is the exact same stuff as year one, but the functions might be a bit trickier to integrate. And already these videos, they're meant to be short and they often get a bit longer than I want them to. So there's only going to be one example with this, and it's the one that feels a bit more unusual with vectors. So at time t seconds, a particle has velocity, this thing here. Now, it doesn't tell us that it's variable acceleration, but because the velocity is variable, it's making us think that the acceleration is going to be variable as well. And the first thing that it wants us to do is to find the magnitude of the acceleration of p when t is 1.5. Well, we've been given the velocity and we want to find the acceleration, so we will differentiate. Now, as usual, I always like to write things in column vector form. So we have 2t squared plus 3t, and then we have 5 plus 2t. Now, you don't even really have to show that you're differentiating. It's implied by what you're doing. So when I differentiate this with respect to t, 2t squared goes to 4t, and 3t goes to 3, 5 goes to nothing, and 2t goes to 2. So we can see it's variable acceleration because this is not constant. This will be changing for different values of t. And they've asked us to find the magnitude, i.e. we're going to do some Pythagoras, of p when t equals 1.5. So when t equals 1.5, the acceleration is going to be 4 times by 1.5 plus 3 and 2. 4 times 1.5 is 6. 6 plus 3 is 9. And so the magnitude of the acceleration, again, it's just so easy to forget doing this last bit, which gives you a couple of extra marks. It's going to be the square root of 9 squared plus 2 squared. Square root of 85, but I'm going to do it as 9.22. Let's give it some units. 2, 3 significant figures. 9.22 meters per second squared. Okay. For part B, it says find the value of t at the instant when p is moving in the direction of 2i plus j. Okay, so we're talking about it's moving in the direction of. It's another one of these ones where we're looking at its velocity vector being a multiple of that direction vector. It's a multiple of it because it might not be exactly 2i plus j, but it could be a multiple of it because it would be parallel then. So for part B of the question, we are going to say that its velocity vector, which is 2t squared plus 3t, and 5 plus 2t, is some multiple of 2, 1. In other words, this part is going to be double the bottom part, but I'll show you it with the k notation, just because sometimes people find it a little bit easier. So we know that 2t squared plus 3t is equal to 2k, and 5 plus 2t must be equal to k. So I'll substitute it in. 2t squared plus 3t is equal to 2 lots of 5 plus 2t. That's 2t squared plus 3t is equal to 10 minus 4t. Great, we've got a quadratic here. So that's going to be 2t squared, 3t plus 4t. I don't know why I've suddenly done a negative there. Let's get that correct as a positive as it should be. 3t minus 4t is minus t, and we'll subtract the 10 so that we have it as a quadratic. We don't have to show how we're solving this, so we can just go straight in and say the coefficients are 2, minus 1 and minus 10 on our equation solver, and t is either equal to 2.5 or t is equal to minus 2, but of course we're not going to accept negative values of time, so t is 2.5 here. Okay, then it says, at time t seconds where t is greater than 0, the position vector of p relative to a fixed origin O is r meters. When t is equal to 0, r is equal to 2/3 I minus 9j. In other words, we've got its initial position here. We're going to start off by finding an expression for r in terms of t. Well, we've got v, we want to find r, that means we need to integrate the velocity. So let's do this. So if the velocity is 2t squared plus 3t, and we have 5 plus 2t, if I want to find out what r is equal to, we're just going to integrate. So 2t squared, I'm going to increase the power and divide by the power. I am going to increase the power and divide by the power. I am going to just add a t on, and I will increase the power and divide by the power. Now, when you integrate, don't forget you're supposed to add constants of integration. If you want to, you could add a c and a d like this. Or, if you want to, you could just say there is a constant of integration that is a vector afterwards. Now, we have been told that when t is equal to 0, r is equal to this thing. So I can do that to find out what the constant of integration is. So when t equals 0, r was equal to 2/3, 2/3 and minus 9. So I'm just going to figure out what c is. So r is 2/3 and minus 9. And when t is equal to 0, you literally just get that that's what the c vector is. So we now have, obviously when you substitute 0 in all of these, they just disappear. So r is 2/3 t cubed plus 3 over 2t squared. And obviously when you add c to it, there's going to be the 2/3 for the I component. And then we get the 5t plus t squared, and there'll be the minus 9, which comes from this bottom part here, okay? I'm trying to go a little bit quicker than I might do in a regular video because these are sort of summaries that we have. Okay, so we've got this expression now for r. We're just going to do the last part, which is to find the distance OP when t is equal to 2. So let's go over to this side of the page, and I'm now just going to say that t is equal to 2. So let's find out where it is when t is equal to 2. I'm literally just going to substitute 2 into all of this. So that's 2/3 times 2 cubed plus 3 over 2 times 2 squared plus 2/3. And then we have 5 times 2 plus 2 squared minus 9. And now you have the fun of just me typing stuff on my calculator whilst I don't really say anything. So 2/3 times 2 cubed plus 3 over 2 times by 2 squared plus 2 over 3. And we get that this is 12. 5 times 2 plus 2 squared minus 9 is 5 that we have got here. And we need to figure out where it actually started. Now, this might make you think, oh, let's just see how far it has travelled. But we need to say the distance between O and... Oh, it's just the distance between O and P, excuse me. It's not the distance from where it started. It is just from the origin. So this is the vector from the origin. I was thinking we might have had to subtract this for the distance it had travelled. But no, that's not what we're talking about. We're saying the distance between this and the origin. So, hence, OP... it's just going to be, this is the relative to O already, it's going to be Pythagoras with the 12 squared and the 5, and I don't even need my calculator for that because it's a Pythagorean triple. So the distance OP between the origin and where it is when t equals 2 is 13 meters. Now I have said at the bottom, I've already mentioned this, but just be warned, you may still have like variable acceleration questions like the same style as year 1, but with some much harder integration type of stuff. Now this is the end of the A-level chapter summaries. This has been a huge project of mine. If you have found these useful, please make sure you're subscribed to the channel. Please like the videos, share them with your friends. All of this stuff is really helpful to keep my channel sort of growing and reaching all the people that I want it to reach. So I hope that you're set up very well for whether it's a mock exam or the real thing, and that these chapter summaries have been a good one for you. Thank you guys so much, and I hope to see you in another video soon.